Energy, Key to Tomorrow, produced by WQED for the Educational Television and Radio Center, in cooperation with the Westinghouse Electric Corporation and the Atomic Energy Commission. The subject, radioactivity. Your host, Dr. Warren F. Witzig, Manager of Reactor Physics, Bettis Atomic Power Division, Westinghouse Electric Corporation.
Hello, my name is Warren Witzig. I'm your host for another discussion in this series on nuclear energy, the key to tomorrow. In this, our third discussion, we're going to talk about radioactivity. You'll recall that in our first get-together, we discussed energy. We learned that there were two kinds of energy, potential and kinetic energy. And at that same time, we learned that the uranium, the source of fission energy, was one of those forms, potential energy. In our second discussion, we talked about matter, and we learned that in reality, matter was merely another form of energy. We also learned about the nucleus of the atom and the sort of swarm of electrons about that atom. We discovered the principles of accelerators. Then we can see that there's really two kinds of radioactivity. The first is natural radioactivity. The fact that the uranium in these bottles are radioactive. The thorium that we have in the earth. Radium, the kind that I have on my watch dial. These are all forms of natural radioactivity. In fact, you and I are radioactive right this moment. And why? Because we are bombarded by cosmic rays from outer space, which produces carbon-14. Carbon-14 is radioactive. Then there's a second kind of radioactivity, artificial radioactivity. And this we produce by accelerators and reactors striking, or rather I should say the particles emanating from these two devices striking the nuclei of other atoms. All right, how did we first discover radioactivity? Well, it happened quite some time ago, in France, in fact, in 1896. There, a mineralogist by the name of Henry Becquerel discovered that the mineral samples that he had were fogging his films. He learned that when he put an object, such as this key, the symbol of our series of discussions, the key to tomorrow, when he put an object such as this key between his mineral specimens and photographic film, he got an impression of that key. Therefore, we learn that there must have been some form of radiation, perhaps something like light, coming from these minerals. We have questions then that come to our mind. What causes radioactivity? What is radioactivity? How can we use and control radioactivity? Well, we're very fortunate. In this discussion, we have with us a man that can answer these questions for us. This man is a senior physicist working at Westinghouse in the field of radioactivity. Supposing we go into the laboratory now and meet him. Hello, Ed.
Hello, Warren.
Let me first introduce our guest. This is Ed Sanford, who's going to talk to us on the subject of radioactivity. What are you doing here, Ed?
Hello, Warren. Oh, just setting up a little demonstration of energy instability. This little wobble toy here, I think, can do this very well.
Fine. Tell me about it.
Well, you see, normally this toy likes to be standing straight up. He's very stable in that position. And if he's tilted, he tends to return to it.
Mm-hmm.
If I add some potential energy to this little wobble toy, he will tip over and get rid of it automatically and return to his stable position, as I can illustrate here. You see?
Oh, yes.
Now, the same sort of thing happens in radioactivity.
How so?
Well, for example, I have a little sketch here. Here's the nucleus containing our neutrons and protons. If some form of energy, this could be an alpha ray, a beta ray, a gamma ray, etc., enters the nucleus, this extra energy makes this nucleus what we call excited. It's unstable. It wants to get rid of that energy. It will do so, again, by emitting an alpha ray, a beta ray, a gamma ray, a neutron, or perhaps a proton. Any of these forms of radiation. This is the return to stability after gaining that excess energy.
I see. Well, tell me more about these alpha particles, Ed.
Well, an alpha particle, Warren, is nothing more nor less than the nucleus of a helium atom. It consists of 4 particles of approximately equal weight. There are 2 protons and 2 neutrons. The protons being positively charged, the total charge on this helium nucleus or alpha particle is +2. Since it is heavy and it contains such a rather large charge, it interacts with matter very strongly, so that its range, the distance it moves through matter, is very, very short. Now, I have here a counter. This happens to be a Geiger counter, which is sensitive to alpha particles, so that I can detect them. It will count them and detect them. And every time an alpha particle enters this counter, you will see over here the lights flash and the buzzer buzz. I also have a source of alpha radiation. On this little aluminum foil is deposited a source which is giving off alpha particles. Now, this has a very short range, as I said, even in air. It's perhaps an inch in air or so. So I have to bring it very close to the Geiger counter before I get any counts. I shall do this. And you see, as I get closer, the count rate goes up. As I decrease the distance, the count rate goes down until it
You do
vanishes.
have to get very close, don't you?
Yes. Now, to show you that the range isn't very great, I have a piece of paper here, and I will show you this is sufficient to stop all counts.
Interesting.
First, I will bring the counter, the source again close to the counter, and I will interpose the paper. And you see that it stops them all.
It's remarkable. All right. Now, alphas. I have a concept of alphas. Now, what about the betas?
Well, beta ray, Warren, is only an electron, our old familiar friend electron, that flows through the wire and gives us electricity. It is a particle which has a unit charge, but in this case negative, but still equal to that of a proton. Its weight is very small. It's about 1/2000th of a proton or a neutron's weight. Now, a beta particle, because it has a unit charge and is very light, has a range somewhat greater than an alpha particle in any material. But it still interacts very strongly with the positive nuclei of matter, so its range is still rather short. It's on the order of several inches in air.
I see.
I
Whereas
can
the
use-
alpha was still shorter.
Yes, oh yes, an inch or less.
Mm-hmm.
My Geiger counter here is also useful for counting beta particles, and I have a source of beta particles deposited on this small piece of plastic here is a beta source. And as I come close to my counter, you see it counts very strongly, and from a slightly greater distance in the case of alpha rays.
Mm-hmm.
You will also see that the shielding required is somewhat greater than for alphas, because my piece of paper will not quite stop all of them.
I see.
I'll bring it up to the counter again and interpose my paper.
And it
you
still
see,
counts a little.
It counts some, but not all.
Mm-hmm.
So that the range of these betas is somewhat greater than that of alpha particles.
Now, why do you keep all of the sources over there, Ed? What do you have there?
Well, Warren, there are 2 reasons, actually. I'm shielding with these lead bricks so that the radiation, not too much of the radiation hits my body. I don't like to be overexposed to it. It's rather dangerous. However, the quantity here is rather small. Also, since I am demonstrating with these counters, I don't want the radiations from these sources to reach the counters and spoil my demonstration. So the lead weight stops most of the radiations involved here. Also, I move them far away so that that cuts down the intensity also at the position of the counters.
All right, now let me see, Ed. We've covered the alphas and the betas. Now there was one more, the gammas, right, that we wanted to talk about.
Well, a
before we
gamma
get to
ray,
the neutrons.
a gamma ray is nothing but electromagnetic radiation. It's not a particle, it's pure radiation. It has no mass, but just energy. It's of the same nature as radio waves or light waves, electromagnetic radiation. The only difference, and the reason we have the different terminology, is a matter of frequency or energy. As the frequency goes up, the energy goes up. At the bottom of the scale are radio waves. There are 1,600 kilocycles on the dial. This is the frequency. If you increase this frequency, or the energy of this electromagnetic radiation, you come to light waves. Increase it still more X-rays, and still more yet gamma rays. So it's very high intensity light or high energy radio waves, if you please. Now, my Geiger counter is also useful for counting gamma rays. And I have a source of gamma rays behind the lead. Now, the gamma ray interacts with matter, but not nearly as strongly as alphas and betas. It goes a long distance, just as radio waves go a long distance from the transmitter. So that almost as soon as I take my gamma source out from behind this lead shield and approach the Geiger counter, you will see that I get counts. And I cannot get too close without saturating my counting system here. Now, my paper, you will see, has absolutely no effect.
Yes.
However, I have here another lead brick. This is sufficiently thick and sufficiently dense to stop almost all of the gamma rays. And I'll show that this is so. As I go behind the lead, you only get an occasional count, as opposed to the very many you get out here. So that we can shield gamma radiation with lead.
Both lead and distance.
Yes.
All right, Ed, now let's see, alphas, betas, gammas, the neutrons.
Oh, we
what
have
about
the
the neutrons?
Neutron, of course, is that particle which is of greatest interest to us in the nuclear energy business. The neutron, as its name implies, is a neutral particle. That is, it has no electric charge. It has a mass approximately equal to a proton, 1 atomic unit. Because of its complete lack of charge, it does not interact very strongly with matter. So its range is very great.
Yes.
It's many, many feet in air or light materials of that kind. I have a source of fast neutrons here, and before I take it out, I will remark that my counter is sensitive, this Geiger counter is sensitive to fast neutrons, and the lead isn't much shielding for neutrons. So almost as soon as I get nearby, you will see a few counts from my fast neutron source. It's quite intense.
Yes.
This source in here is a source of fast neutrons. That means they have high energy or high velocity. Now, I have a counter over here, which is called the fission counter. And let me turn this one off so that it doesn't give us any trouble.
All right.
This counts only slow neutrons, not the fast neutrons, which come from this source here. As you see, there are no counts as I bring it close by.
Is it safe for you to handle that like that, Ed?
Oh, yes, the intensity of this is very low. I wouldn't want to carry it the rest of my life, but for the short times here, it's quite all right. Now, in nuclear reactors, the neutrons that cause the fission are slow neutrons. And when the fission occurs, the neutrons that are born in fission are fast neutrons. So somehow they must be slowed down. Their energy must be decreased, their velocity must be decreased to be useful again in causing more fission. So we use what we call moderators. This piece of paraffin is a moderator. When a fast neutron enters it, many collisions take place, slowing the neutron down, taking its energy away, and the neutron emerges slow and can then be counted by my slow neutron counter. And I will illustrate this. I place my paraffin before the counter. I hold my source up above it here. You see there are no counts from the fast neutrons. But as I get behind the paraffin, so these fast neutrons are slowed by the paraffin, moderated, and enter it, you will see we'll get some counts.
Oh, yes.
It's a process of moderation. Now, in order to control nuclear reactors, we must have some way of getting rid of these neutrons that are causing a chain reaction, these slow neutrons. Some materials, such as this cadmium I have here in sheet form, absorb slow neutrons very readily. So they remove the neutrons from the nuclear chain reaction and control it. Now, cadmium, however, does not, by any means, absorb fast neutrons. I will put this cadmium around my fast neutron source here, and you'll see it'll have no effect whatsoever. The fast neutrons are going right through it. However, if I place it around my counter, between the slow neutrons emerging from the paraffin and the nuclear counter, it will stop the counts completely, showing that the slow neutrons are being absorbed.
Within that cadmium. I see.
I'll remove my source.
All right, fine, Ed. I have a pretty good idea now. We've talked about the alphas, the betas, the gammas, and the neutrons. Now, I'd like to learn how to use and control these radiations. How can we do this?
Well, Warren, I'll have to say a few words first about the properties of matter so that we can understand how we control our hazards. First of all, matter consists, as you know, of a number of atoms arranged in space. However, most of matter is empty space. There's long distances between the atoms.
Yes, we discussed that in our matter episode.
Yes, so that any radiation entering matter can travel quite a distance, this is the range, before it is stopped and loses its energy, because most of the time it completely misses atoms. However, when collisions do take place, energy is transferred from the radiation to the atoms, and the radiation then goes on with a lessened energy, and this may happen several times before the radiation's energy is all used up. I have here a small diagram which can illustrate what we call the decay of radioactivity. The decay in intensity, or a quantity of radioactivity that is available. Here I have plotted the intensity of radioactivity, or the number of radioactive nuclei, versus time, where time is measured in what I call half-life periods, 1, 2, 3, etc. The characteristics of radiation are that if you have a unit amount at time 0, say right now, in one half-life you will have 1/2 that amount present. In another half-life, 1/4, and so on, multiplying a half each time. So decay in time goes like this.
Well, does that mean that all of these, now wait, does that mean that all of these radioactive isotopes are going to decay in the same fashion?
No, this half-life period is unique with each isotope, and it may vary anywhere from split seconds to many millions of years. Each isotope has its own decay period, so decays at a different rate. But the shape and the characteristics are the same for all radioactive nuclei.
I see. All right, then, you've given me some background now on the use and control of this, but just how do we use it, and just how do we control it?
Well, an example of use in the atomic energy industry is in what we call the hot laboratory. In the hot laboratory, you have a number of what we call hot cells. In each of these cells is a highly radioactive material which is being manipulated in one way or another. We see men before each of these cells who has remote control tools which he can do all milling operations, all machining operations, all laboratory operations quite remotely and safely, because he has before him a shielding wall, which stops most of the radiation. He has a shielding window.
Much like these lead bricks that we have here on the table.
And he is furthermore removed in distance from the source.
I see.
And by doing everything remotely, he can do it quite safely. And these instruments are quite sensitive, quite delicate, so that you can do all the operations you normally do when things are right in front of you. Now, another illustration of this is the case of where we use a deep pit of water to handle radioactive material. That is, we see men who are lifting up a lead cask. In this lead cask is some radioactive material. The lead is acting as a shield, and as also the pit of water did. These men are protected by protective clothing. We see a health physicist who is monitoring with the Geiger counter to see that the whole operation is safe for these people to do. And they also are held off by railings at a safe distance from the radioactive material. Now, we also have a health physicist shown. This man has protective clothing on him. He has polyethylene plastic shoes. He has a respirator. This keeps the radioactivity off his skin and also out of his body by breathing it. He also has put paper on the floor in this hot cell so that no radioactivity will spill around the floor or any that's on the floor be picked up by his shoes. Furthermore, he is monitoring with the Geiger counter to see that people who are going to come in to work, it is safe for them to do so. These are the regulations and techniques which we use.
I see, Ed. It sounds very, very interesting. So we use then distance, and we use shielding, protective clothing to keep this radioactivity away from us, as it were. Now, I noticed that you're wearing a film badge.
Yes, this little device here contains a piece of film which, when exposed to radioactivity, will darken.
Much like Becquerel's original discovery on this.
Yes, I might illustrate one of these methods that we've used here for safety, the concept of distance. If you have a radioactive source at the center, and let's say at a distance of 1 foot away, the radiation intensity is 16 units.
Mm-hmm.
If I double this distance, making it 2 feet, the intensity drops down to 4 units, or the square root. If I again double the distance and make it 4 feet, the intensity drops to 1 unit. This shows a very rapid decrease in radioactive intensity with distance. And so I can walk away from these sources over here and get protection from them. My film badge doesn't show any more exposure. And, of course, my lead bricks are an illustration of shielding. So that, to be perfectly safe, I put my shielding and stand back right away. And then I don't run into trouble by having my film exposed and darkened, showing that I can't work around here anymore for a while.
I see. All right, then, let's recap, Ed, for just a moment. Radioactivity, what causes it? Well, we've learned that it's the nuclear instability. We remember our little wobbly toy. And then we've asked the question, what is radioactivity? We've learned that it's composed primarily of alpha particles, which is really the charged helium nucleus. We've learned that it can be beta particles, which is our old friend, the electron. We've learned that it can be the gamma rays, which is really another form of light energy.
Electromagnetic
radiation. And we've learned that it can be neutrons. And of course, in this series of discussions, the neutron is of vital importance to
Oh,
us.
I might add that fission itself is a form of radioactivity.
Yes.
You see, the particle in this case is just as big as the nucleus left behind, but it's nothing different. You add the extra energy in the form of a neutron, and the uranium nucleus starts to pulsate and splits right in half.
I see.
Exactly as in the case of our nucleus here, only the pieces are much larger. It's no different, however.
I see.
It has a very short half-life, millionths of a second, I might add.
And then we're learning to control and use this by the methods of distance and shielding, that is the interaction of radiation with matter.
Yes.
Fine. Then there's the tolerance problem. How much radiation can you and I safely absorb?
Well, we have a unit we call the milliröntgen, which is a very small unit, and we're allowed to accumulate a maximum of about 300 of these every week in the industry. And this is, well, it gets to a point where it's almost unworkable. We need lots of men because if they get overexposed, they can't work for another week or something like that. But we're exceedingly careful, and the tolerance doses are approximately 1/10 of what we know is safe.
Fine, Ed. I'd like to thank you, Ed, on behalf of the viewer and myself for taking time in your busy schedule to tell us about radioactivity. And I'd like to close with the viewer in this way, saying that We are going to have another discussion in our next series on nuclear energy, the key to tomorrow. And that discussion is going to be the history of the fission process. At that time, we're going to have a very distinguished guest who is the scientific editor of the New York Times, William L. Lawrence. Until then, I would like very much to ask you to join us on our next discussion period, our discussion period dealing with the history of nuclear fission.
Nuclear Energy, Key to Tomorrow, produced by WQED for the Educational Television and Radio Center, in cooperation with the Westinghouse Electric Corporation and the Atomic Energy Commission. The subject, radioactivity. Your host, Dr. Warren F. Witzig, Manager of Reactor Physics. Special guest, Mr. Edward R. Sanford, Senior Physicist, Bettis Atomic Power Division. Technical advisor for this program, Mr. Raymond R. Schiff. Engineering supervision by Frank Stuckman and Stephen Zorbas. Production and direction for the series by John W. Ziegler and Robert E. Potts. This is National Educational Television.